with us. Please wait for a few minutes. We will start our meeting soon. Thank you.
Saya, I think you can start off.
Yeah, go ahead.
Good evening to one and all. Imagination is the foundation to all invention and innovations. I'm Saya Fatima. I'm here with immense pleasure to welcome you all to the webinar on design and sizing of solar photovoltaic plants for residential applications conducted by IEEE PES SBC SJCET. Thank you everyone for being here with us. We are glorified to welcome our today's speaker, Ajith Gopi sir, Joint Chief Technical Manager. Currently is heading Technical Consultancy at ANERT, Department of Power, Government of Kerala. And he is an IEEE Senior Member and Vice Chair IEEE PES Kerala Chapter. It's so grateful to have you here, sir. Thank you so much for being with us. Now, I welcome Hannah Susan Matthew, IEEE PES SBC Chair, for the welcome note.
Thank you, Saya.
Hi all, good evening. So I'm Hannah Susan Matthew, Chair of IEEE PES SBC SJCET Palai. Hope you all are safe and sound, and thank you for showing up this evening and supporting this event. So it's my honor and privilege to propose the welcome speech on behalf of IEEE SJCET Palai. Once again, I welcome all of you to St. Joseph's College of Engineering and Technology Palai IEEE Student Branch online online webinar session. So far throughout this COVID pandemic, we have been through a series of tech talks and events which molded the audience as well as the host to a great extent. Today, we are virtually gathered to attend a technical webinar on the topic Design and Sizing of Solar Photovoltaic Plants for Residential Applications, hosted by Power and Energy Society chapter of IEEE PES SBC. Let me now move over to my duty. First of all, I would like to welcome the speaker for today's webinar, Mr. Ajith Gopi, Joint Chief Technical Manager, heading Technical Consultancy in Solar PV Projects and Wind Energy Program at ANERT, Department of Power, Government of Kerala. He has got more than 30 years of experience in renewable energy field. He is a senior member of IEEE and currently Vice Chair of IEEE Power and Energy Society, Kerala chapter. He has also mentored a lot of students. He is also a member of International Solar Energy Society and International Expert Network in Renewable Energy. He has been trained by Life Academy, Sweden for wind power development and use. He is also trained in National Institute of Solar Energy and National Institute of Wind Energy in both solar and wind energy field. He is currently a PhD research scholar in the State University of Malaysia in the field of renewable energy and environmental engineering. With his multiple roles and his spirit of community, he has been truly inspiring mentor. It would be my great privilege and honor to welcome him to the session. I welcome you, sir.
Thank you, Hannah, for the nice introduction. Hope I'm audible and visible.
Yes,
Can you
sir.
confirm?
Yes, sir. Yes, sir. You're audible.
Great. So, hello, St. Joseph College of Engineering and Technology, fellow IEEE volunteers, IEEE PES volunteers. How are you doing? Hope you are all fine against or amidst of this pandemic. So I'm very glad to be here speaking to you on a subject which is very hot topic now about solar energy. So without much introduction, anyway, I'm grateful to the organizers, and of course it is my duty as the vice chair of IEEE PES chapter, but it's a real privilege to be speaking in this nice evening. Yeah, let me share my screen first. Can you see my screen? Can anyone confirm?
Yes, sir.
Yes, sir.
Okay, perfect. So I'll be speaking on design and sizing of solar PV power plants for residential applications. As Hannah was introducing me, and actually she was asking me which subject I wanted to speak. So generally, I was speaking on mostly recently on resource assessment, microgrids, and on strategies, maybe something like prospects. So as students, I thought I'll give you some of my thoughts, some of my lessons on the design and sizing of solar power plants. It will be useful for younger students, young graduates, and the aspiring engineers and scientists. So you can see a picture here in my beginning slide itself. This is a rooftop, a big rooftop power plant we recently installed at third phase of Trivandrum Technopark. You could see two buildings. Actually, it is installed in a twin tower building, a Ganga Yamuna building in the third phase of Trivandrum Technopark. 100 kilowatt in Ganga and 100 kilowatt in Yamuna under the technical consultancy scheme of ANERT. Wonderfully working. This is actually a mid-size solar rooftop program. So solar rooftops are very common now. A lot of solar projects are being constructed all over Kerala in residential houses or in homes, plenty of them. And of course, in industrial premises, industrial rooftops, commercial rooftops, a lot of power plants are being constructed. So I think it will be interesting for you to listen to me on the same subjects. I'll give you a backdrop of this session with a couple of slides. I will tell you that more than 1 billion people are without access to electricity in the world. That is why UN has come up with a sustainable development goal. There are 17 sustainable development goals framed up for this particular mission. And poverty eradication is one of the highest priority missions under the sustainable development goals. SDG 7 has a priority. It is speaking about the access of energy to the people, especially about the clean energy. So it's very interesting to learn, especially in the context of more than 1 billion people, especially people from sub-Saharan Africa and from Southeast Asia are without access to electricity. A lot of people a lot of communities are still living without access to conventional electricity in India as well. This is a serious problem actually, because modern energy access is very important for the economic development of people. It's very essential because that will define their prosperity. So energy poverty is a reality. As the great Nelson Mandela said, overcoming poverty is not a task of charity, it's an act of justice. So overcoming energy poverty is same as well. It's an act of justice. For overcoming this energy poverty, renewable energy is the best solution actually, especially solar energy, because solar energy can do wonders. I had a chance to travel to Tanzania in Africa, part of a government program, part of the Swedish Academy fellowship. I was selected for one of the solar wind hybrid workshops there a couple of years back. They took me to the remote areas of Tanzania. We could see a lot of areas where there is no conventional current, conventional electricity. They have wired up these remote areas, some of the areas, hospitals, and all with the renewables, especially with the solar energy. ANERT also participated in the remote village electrification program. We had a great program initially in 2000-2003, part of the MNRE program, ministry's program, to wire up remote tribal colonies. We wired up around 20,000. It's with a very short time you can install these systems. They are it's clean. You can have decentralized solution. You can have modular design possibilities and smaller deployment possible, easy maintenance. So the wonderful systems which we can install within a very short gestation. Clean energy, of course. So we will be contributing to the SDG 7. Seventh Sustainable Development Goal. Isn't it interesting? Coming to our state imports more than 70% of its electricity from the central grid. And we are generating only 30% of energy internally. So we have to be self-sufficient in terms of energy. It's very important for self-reliance. We always speak about self-reliance. So energy is an important part, as I told you about energy poverty. So modern appliances will be working on energy. It will be solved by electricity. So we need more power or we need to be self-sufficient in terms of energy generation. So that's why State Urja Mission targeted 1000 megawatt by 2022. Out of that, 500 megawatt from the solar rooftop program. This is actually targeted at residential rooftops. In the state, ANERT and KCB is spearheading the program. We have different targets for achieving this 500 megawatt quickly. The attraction is we couldn't go for the higher scale ground-mounted solar power plants in our states because we don't have that much of space available. So we have to invest more into the rooftops because that is because the decentralized systems are very common globally now. DER, it's short named as DER, distributed energy resources are very important. They are doing very important role in the market now, in the global energy scenario now. So especially this distributed energy resources and distributed energy is making wonders because of the advancement in technology. It can be primarily solar, it can be wind energy as well. A lot of distributed energy resources are being connected to the grid, and the research happening on this side, especially on the blockchain side, on the innovations on technology are leading to the distributed energy generations. Of course, it is making some issue to our central, our usual grid. When you pump a lot of distributed energy to the network, there will be issues. But these issues are now being solved. We have excellent forecasting techniques. We have a lot of grid management systems to control. So assessing your solar resource is very important for designing it. So based on a basic evaluation of your solar resource using Meteonom software. Meteonom is a software. It's a private software. They provide data from satellites of solar resource data. Around 5.5 kilowatt hour per meter square per day. That means square meter you will get 5.5 units of energy. I will repeat. In a square, you will get 5.5 units of energy. Okay. So it's pretty good figure actually when compared to the Northern European countries. If you compare this with the Scandinavian countries, or if you compare this with the Stockholm in Sweden, there you will have around 3.5 units of electricity per square meter per day. So comparing to that, so if you count it to an annual figure, it will be around 2,000 in Kerala. Pretty good figure. It will be something more higher insulation or more higher sun peak hours you will get in Rajasthan because it's more sunny days available. Okay, fine. I will come to this. Of course, I'll be giving an overview of the rooftop systems, solar rooftop systems, standalone rooftop systems. I already described it was preferably installed in remote tribal colonies or remote areas in Kerala, but this has come common in urban areas as well. We have a lot of systems with the battery backup. We call it as off-grid systems or standalone PV systems, mostly installed in rooftop. And grid-connected PV systems, it's very common. A lot of systems are being installed. You all are familiar. I know a lot of people having rooftop systems there. And hybrid PV systems will be something like you have a hybrid inverter. You have a system with intentional islanding. Your hybrid inverter will have a capability of connecting or plugging a battery into that. So those are having the same kind of certifications of grid-connected systems, but at the same time, it will have an intentional islanding scheme where you can, it will be islanding whenever your PV is or your grid is off. So it's a kind of dual application. It can be an off-grid system, it can be a grid-connected system. So whenever the grid goes, it will island itself and give you the power, the critical power. Those are hybrid PV systems. I'm not detailing much into the about solar modules and all. I'm skipping this. So coming to the tilt of the PV module. So I'm directly jumping to the concepts, design concepts, because as younger graduates or younger, I think 7th semester student or 8th semester students, this will be interesting for you. Generally, there will be tilt for the PV modules or solar array when we install solar power plants. The orientation and tilt is very important. I will start with the orientation first. In northern hemisphere, where we are living, the orientation is we face the solar modules towards south, right? Because sun will be in the other horizon. But in Australia, it will be in the southern horizon. We will be facing the modules facing north. So in India, most of the time, in Trivandrum, you can see sun coming to the northern side, over our head, and some months it goes to the north. But when you take Andhra Pradesh or Gujarat, it will be always south. So when you take the northern hemisphere, the thumb rule is you have to orient your solar PV module towards south. Okay, lesson number 1. I'm not going to azimuth now. I'll go to azimuth later. Okay. It will be a bit complicated at the moment now. And about tilt, these are the basic things people usually make errors in installation. I have seen a lot of systems with more than 25-degree tilt. What is the tilt you can take for your solar PV module in Trivandrum or Kollam or in Kerala generally? What actually the advantage of inclining or tilting your solar PV module? Of course, you are orienting the PV module towards south, right? This will give you an illustration. You have incoming toll rays coming from the sun. If you make the solar module in this way, you will get maximum solar rays, toll rays falling on it. And if you make it horizontal to the plane, you will get only 9 rays, right? This is simple illustration of how you have to make a tilt to get maximum advantage of the total rays coming up. Okay. And I will give you some thumb rule for that. I'm not detailing much into my younger students. There are a lot of complicated equations for finding your right tilt. But if you refer journals, you have a lot of journals telling about finding the optimum tilt of solar PV. You just go for a research for Science Direct journals or IEEE journals. You will get a lot of journal papers. For finding the optimal tilt, we can refer a lot of reference regarding, you can go for the degree which is parallel to your latitude. For example, your latitude is 10 degree. You make a tilt of 10 degree to the horizontal, right? This is lesson number 2. So first lesson was orienting towards south. Remember it? My second lesson is your tilt angle will be equal to the latitude. As a compromise, it's a fixed tilt. Remember, it is a fixed tilt. It is not a tracking. You have single axis tracking, you have double axis tracking in PV systems. Single axis tracking will be something like your solar panel will be tracking the sun from east to west, right? The sun rises in the east and goes to the west. So it is single axis tracking. If you add seasonal tracking also from north to south tracking, it is another axis tracking. So both, if you combine it, it is called a double axis tracking. I was fortunate to work in around 20 megawatt in Portugal on a double axis tracking project when I was working with a consultancy program. At that time, we found that around 30% of advantage generation, more than 30%. It was actually for a Korean client. We, from the studies and actual results we got, around 30% plus extra energy generation because of the double axis tracking. In Europe, tracking will be more advantageous. But in Indian conditions, I would say that of course you will get extra energy, but normal tilt, fixed tilt will do a lot. You can have seasonal tilt also. Seasonal tilt will be, Wipro was the client and we were the consultants for, we were working for PB. That project, I was there for exactly 1 month during the installations of the 25 megawatt project. The adjustment they have done is, there are 2 clamps. From October to February, they will have a clamping arrangement, which will give a tilt of 37 degrees. The usual tilt of will be 22 degrees because of the Charanka area latitude, Gujarat latitude. It is near to Fuji actually. Fuji, you may be remembering Fuji, where the earthquake struck into in the beginning of 2000. So 22 is the latitude of Gujarat in that particular area. So the normal fixed tilt will be 22 degree, right? Right. Just like our, in Ernakulam, we will be having a tilt of 10 degree. Gujarat at 22 degree centigrade, so 22 degree tilt, because the latitude is 22 degree there. So where in Charanka Park, we did a tilt of 37 degree during the period of October to February, during the winter period. So that was an adjustment plus 22 plus 15. So as a thumb rule, then you look at this slide. You have latitude plus 15 tilt, maximizes fall and winter performances. It maximizes actually. And the same, we have laborers there, our O&M people will be arrange this tilt from March to September. Based on my initial studies conducted in that park, we gained around 10% extra generation because of this manual tilt. But there was some disadvantages because this clamping kind of adjustments can make some hardware issues. Of course, if you handle it very roughly. So I would say that a fixed tilt can bring a lot of power to Indian conditions because you have a lot of, and latitude minus 15. So what happened during the summer in Gujarat was like 22 minus 15, they put it at 7 degree tilt, right? This is a fantastic example I will tell you about how, as a thumb rule, you will make a kind of seasonal tilt, right? And azimuth, I'm not complicating things, but azimuth and your azimuth will be something like, I would say that when sun moves, azimuth changes actually. It's actually, it's an angle from the north, south, what do you call it? If you draw a line between, from your true north to true south, from that how the angle differs from of your sun's position will be the azimuth. So there are different conventions for that. If you go to west, it will be minus, and you go to east, it will be plus. There are different conventions taken for different softwares when you go for simulations. But that will be considered when you go for the simulations. For example, I have a rooftop. My rooftop is actually, I have a Becker model house construction, tilted roof. I have a lot of rooftop on the western side and in the eastern side. I cannot go for concentrating my solar panels on the southern side itself because I have a few space for southern side. So I have to utilize my western side. So if I put my solar module on the western side, and if I'm going to simulate in PVSys or PVSol or any other kind of software, I'll put the azimuth as -90, right? I'm not experimenting with any software here. I have taken a lot of sessions on software simulations. You can maybe listen to me on various occasions. But I'm telling how I am using this azimuth in that particular software simulations. If I orient my solar modules towards west, I will put my azimuth as west. If I orient towards south, I will put as 0. If I orient towards east, I will put as +90. So which will give some different kind of fields. So we can have a comparison of how your south-facing module will provide energy when compared to your west-facing module and your east-facing module. It's an interesting subject to learn and research, actually. I guess some of you can do some experiment on it. Okay. A grid connected system, a typical simple illustration will give you the solar modules. You have a junction box. This is a simple kind of illustration. You have a junction box, a DC junction box, DCDB, or kind of, this is not called a DCDB. It's called a string combiner box or junction box. There are different terminologies used in the industry. Junction boxes, JB or SJB, or what you call string combiner boxes, SCB. There are different terminologies people call it. All these SCB string combiner boxes will have some safety accessories as well. You have a surge protection device will be there. SPD will be there, and your DC cabling go to the solar isolator. There will be an isolator will be there to isolate your solar array from that side, and you have an inverter, AC cabling. Then you have the AC side and isolator and a energy meter. This is a simple illustration. Not going much into the details, is to give you younger students an idea of what actually happening here. Okay. I'll give you a real example of one picture, which peak there. I'll come to what peak later. Okay. You see the environmental benefits. It's avoiding the release of about 160 tons of carbon dioxide from the atmosphere. Okay. And this picture will be very interesting. I took it from the 100 kilowatt solar power plant SCADA. A single day generation, it's a typical generation log from a single day. You can see two type of graphs there. The red color is the kilowatt hour, and the yellow colors or orange color is watt per meter square, your irradiation. This will give you an idea of exactly, it's a kind of bell curve. Your solar irradiation and your solar generation is a kind of bell curve. It starts from the morning, it peaks during noon, and it ends up in the evening. You can see the ups and downs because of the clouds. This happens in tropical climate, in Palakkad, in Trivandrum, in Kerala, generally. But in Tamil Nadu, if you look at Chennai, it will be completely different. You don't have this kind of more dips and ups will be very less in Chennai, in a kind of dry climate. I'll go to this slide more because I have a lot of slides to tell. This is another rooftop, just to give an example of a rooftop, 200 kilowatt rooftop power plant we installed in as part of the technical consultancy scheme in Thrissur Corporation. You could see an idea of how it looks like. Here, we had 8 numbers of string inverters and more than 700 PV modules. It avoids around 340 tons of carbon dioxide for the atmosphere. Small power plants can do a lot of job on the environmental side. Isn't it interesting? So yeah, it gives more details of how it is environmentally interesting. You might have heard of Red Screen. Red Screen is an interesting software. I recommend all the students to go to play around it. Download a free version of Red Screen Expert. 8.1 is released now. Red Screen is a Canadian software, very interesting software to do the analysis, energy analysis. It will do a resource assessment as well. You can just play around it with the trial version for 1 month. The Red Screen Expert is the latest one. I have given guidance to some of the engineering students, some of the engineering batches who approached me on Red Screen. They made simulations on Red Screen actually. Why I'm telling about Red Screen is very interesting to give you some of the typical magical numbers like this, like how it is environmentally interesting. Okay, so that was a kind of some ice cream in between the very kind of raw classes, I should say that. This may not be much interesting for you, the numbers and graphs and all. So that's why I'm giving some of the pictures which are live installations, which will be more interesting for you. I remember the days I have given a live, I think it was a virtual IV to some of the engineering colleges. I think it was for the whole IEEE PES student group. It was a student session, bigger session. Where I took a IEEE PES, that was a virtual tour. I took these people, all the students into our 2 megawatt solar power plant installed at Kudalmandam. It was actually a virtual tour. So that will be very interesting for you guys than going to the graphs and diagram, but you have to learn a lot on this side also. I'll in between speak on the other things also. Okay, coming to the basics, characteristics of PV module. So I'll be giving some basics here. Some of my colleagues and some of my young engineers working with me is also joining in this session. Excuse me for this very basic sessions because this will be interesting for the students. That's why I'm giving more details on this side. Okay, this is the basic IV curve for a solar PV module. You will have a short circuit current for a PV module, which is the highest current coming. If you short circuit a PV module, and you have an open circuit voltage, and this is the IV curve actually, and there is a point when you when you connect the PV module to some load, you have IMP and you have VMP. Then your maximum power point is this. And you might have heard of maximum power point tracking, MPPT. I'm not explaining much about that because of the time constraint. So there the tracking is done for the maximum power point. This is a power curve of power versus voltage. This curve will be, both curves are together here. You can see the maximum power point. Which is the corresponding IMP. This ISC, interesting thing is short circuit current and maximum current and open circuit voltage and maximum voltage you can get from your data sheet of PV module. If any solar module, smaller capacity or bigger capacity, you take any solar PV module, on the back side you could see a small kind of your DC template there, and there you will have these things there. You can read out these things. Okay. So this characteristics IV curve you can plot with a small kind of experimental setup, and provided you should have a constant irradiance. So if you have a constant irradiance and you have an ammeter and voltmeter and you have a rheostat kind of thing for varying the current and all, so you can have a IV curve plotted with this characteristics. This characteristics of solar cell can be drawn with this setup. So coming to the equivalence certificate of a solar equivalence circuit. It's not certificate. Excuse me. So equivalent circuit of a PV module.
No problem, sir. No problem.
It's very interesting. I'll just correct it.
Sir?
Equivalent.
CIT.
Yeah, okay. Thank you. It's very interesting. So I'll save it and play from the current slide. Okay, is it visible?
Yes, sir.
Yeah, okay, great. So this is simple equivalent circuit of a solar cell. I remember the days I used this equivalent circuit for my MATLAB simulation during my MTech days. So I thought of I thought actually simulating a typical solar cell, a solar array. Those were there in my computer, but I couldn't get time, so that it was interesting. Modules there, maybe once I will in PS, any other session I will simulate it in MATLAB and show you. Okay, so a simple your solar cell can be represented with this kind of setup. You can have a current source, and you have a diode, and you have a shunt resistance and series resistance. With that, I will just explain. There will be parasitic resistance in the solar cell because of the conductors going there. I'm not going to the photovoltaic effect or PN junction physics. I think most of young engineers know about it. So the parasitic resistance, because the conductors will be the series resistance represented as RS. If you have more series resistance, your current will be less. So it's not good that you have more resistance. And like that, if your shunt resistance is lower, it is better. So this is actually a representation of your equivalent circuit of a solar cell. So if you look at a solar PV module, very important factor is a fill factor. Fill factor is nothing but it's actually a ratio of your IMP VMP by ISC VOC. You remember what I said about IMP VMP, maximum current and maximum voltage. When it is loaded, this is coming. Divided by short circuit current and open circuit voltage will give you the fill factor. Fill factor will be around 0.7 to 0.85 in most of the PV modules now. It was around 0.6 to 0.7 in earlier PV modules because of the high efficiency. So fill factor is a very important factor. This is the squareness of your IV curve. You heard about the IV curve. So if it is more square, you will get a higher fill factor. It's actually a higher your higher fill factor will give you a higher efficient solar PV module. Just remember that. And coming to a temperature versus PV cell performance, this is actually academically interesting. Though it is very dry, just listen to this. When your temperature goes up, there will be issues with your solar PV module. The cell performance will be going down. See the IV curve during 0 degrees centigrade. See at 25 degrees centigrade, the voltage is coming down, right? But a small increase in current will be there. A small, it's not much, very small increase in current will be there. But here it comes down, and because of that, your PMP will be reduced. Your maximum power will be reduced. And this is another variation of characteristics with the irradiance. Irradiance, it's actually linear, I should say. Current, if you reduce your irradiance, this is 1,000 to 50 kilowatt per meter square. So if your irradiance is down, you will get lesser output actually. But voltage is much, when your solar installation goes down, your voltage will be almost there. That you can see from, you can just experiment with your solar PV module. It will be something almost there. You can see that there is less change, but current will be drastically reducing. Very important thing, lesson for you. And these are the very important things. I was telling about the peak work, watt peak. When you rate a solar PV module, for example, 380 watt peak solar PV module, 580 watt peak solar PV, we engineers always define solar PV module like that. So STC is standard test condition, and NOCT is normal operating cell temperature. Nominal operating cell temperature. So standard test condition is actually the set test condition. Here actually, one thing. I will just take up this cell temperature, and you have the insulation. You have the solar radiation. Of 1,000 watt per meter square meter. Fine. Yeah. So STC is actually cell temperature of 25 degrees centigrade, air mass of 1.5, your solar radiation of 1,000 watt per meter square meter. Air mass is actually cell temperature. You understood. But you don't have this kind of ideal cell temperature at your location. Especially when we will be very high. So these are conditions. You go for that 20 degrees centigrade, your cell temperature will go plus 25 degrees centigrade. It can go up to plus 20. Maybe it is reaching 45 degrees centigrade or 50 degrees centigrade at times. And irradiance of 800 watt per meter square, and mean speed, it's more realistic condition, but it's not realistic in terms of ambient temperature for us. So generally Europeans define this kind of standardized conditions. That's why the 25 degree air mass is something like, it's nothing but it actually the distance of solar radiation reaching down in a particular particulate atmospheric condition. It's some ideal condition, some condition, mid condition they have selected. So it's taken as 1.5, a typical atmospheric condition for rating your PV module, right? And 1,000 watt per meter square is actually the solar radiation at the sea level. What is solar constant? Solar constant is 1367 watt per meter square. 1,367 watt per meter square. It is on top of the our atmosphere, top of the atmosphere. It's around 1,367 watt per meter square. But on the sea level, it will be 1,000 watt per meter square. Okay. So standard test conditions are used for rating your solar modules. We have solar simulators which provide this kind of typical atmospheric conditions for testing your solar PV module. And nominal operating cell temperatures are selected for getting some realistic pictures of the actual conditions. Air mass can be calculated by, see, this angle theta is 48.2. The angle of solar from, if you make the sun top and make the total tilt here, take an angle theta, then AM will be 1 by cos 48.2, which is 1.5. This here 1.5 is taken as the air mass. This is a simple block diagram. I have given you some pictures of a grid connected plant, a schematic kind of picture. This is also a simple block diagram for a, just to understand my younger students, non-core professionals, PV array, junction box, you have a solar isolator, you have a inverter isolator, you have energy meter, you are a net meter here. It's not a kilowatt hour meter, it will be a net meter kind of thing, we call it here. This will give you an SLD, typical SLD concept only. I'm not detailing much, a solar PV array. And this I took from a textbook so that it will be on the either this side, the solar PV array is coming. You have an isolator, the basic concept, just to understand that you have a, this is the basic picture. I have seen a lot of SLDs. People say that it is SLD. SLD should be showing the exact symbol of solar PV module. This is the usual symbol for your SLD. You have an isolator on that side. You have a DC isolator. You can have an isolator at the rooftop side itself. You can again have a DC isolator in the string combiner box. Then you have the inverter. Then you have another AC isolator. You can have the main switch. Then your net metering unit and feeding to the power. Okay, then of course your domestic circuits. Just to give you an idea of what exactly is happening. Just to give you an idea of a typical solar rooftop, the typical depiction of your solar cell, solar module. Here a multiple MPPT solar plant. Multiple MPPT is nothing but you have 2 MPPTs or more than 2 MPPTs where you can have different kind of solar strings can be connected. For example, I told you about my solar rooftop. I have a lot of rooftop facing west. So I can put all the solar panels on the west to the MPPT1 and all the solar panels to the south to the MPPT2. It won't make much problem. The earlier single MPPT inverter cannot work here. So if I have a multiple MPPT inverter, then I can connect different orientations, characteristic solar PV modules to my inverter. So you will have other fuses, your SPDs, surge protectors, and your circuit breakers. All this stuff will be there. Sorry. Then you have a DC DB will be there. Your AC DB will be there, where you will have again an SPD. SPD is surge protection device to protect you from the surges. And then based on all this, based upon your current rating, all these systems will be designed based upon your current rating. I'm not going into the switchgear and protection rating. I will just give you a thumb rule of that. When you go for a design of your breakers, generally the thumb rules you will go for you design it for 1.4 times of your short circuit current, total current on that complete string. So if you take a string and you have to go for, take your short circuit current of that particular string. If you take a module, it will be, we always circuit voltage. If you take a string, you take your total string short circuit current of your string. If you take the whole array, you will take the total short circuit current and design it. You multiply with 1.5, and this extra precaution you are taking because of the extra stuff or extra power current can come because of the reflections or the temperature issues and all. If the temperature is going lower, you have higher radiation coming up, right? Higher generation coming up. So this is a typical, I'm not much detailing on this side because it will take much of my time. We are almost approaching time, but I'll take another 10 minutes to wind up my session. So if you look at the specification of solar PV module, you will have you have monocrystalline. If you look at the crystalline solar modules, you have polycrystalline modules, you have monocrystalline modules, and the recent PERC modules, mono PERC modules are coming up actually. Mono PERC modules will be something like emitter rear collector, a technology where you have a collector here on the top in the usual kind of PV modules. If you have another extra collector on the rear side, it's called a passive emitter rear collector. So it will give you more efficient, more kind of absorption of your photons, which will give extra efficiency of your solar modules. So monopod modules with a half-cut kind of arrangement will give more space for your solar cells to display around your solar module, which can give a higher efficiency of 23% for your solar PV module. And just remember that the usual kind of PV modules can have a first-year degradation of 2.5%. And the next year degradation will be 0.7% from second year onwards. The first year, your PV module plant will be degraded up to 2.5%, even more. So beware that if you have a solar plant unutilized, not utilizing, just erected the solar PV module or solar array there, leaving it for 1 year, it is waste of money. How? Because you are wasting money because the first year's degradation is huge. You are not utilizing the first year's advantage of higher energy generation. After first years, your 2.5% will be lost. Fine. So remember that whenever you deploy your PV modules, immediately you charge it up. Don't put these modules as such for prolonged years. 1 year itself will have a loss of 2.5% of energy. It's not good. So then onwards, you will have 0.7% from second year onwards. It's a usual thing. But in the current advanced solar PV modules, even 0.5% I have seen from data sheets. So there are PV modules which give a kind of more module, maybe general warranty will be around 10 years, but performance warranty will be 25 years as per the ministry's, central ministry's notification. 10% of, at the end of 10 years, you should have at least only 10% of degradation and only 25% of degradation at the end of 25 years. That is a guideline from MNRE. So just remember that it's very important that whenever you deploy your solar panels, immediately charge it with all the facilities and all. Don't degrade it. Don't allow it to go for the first year degradation. Why is this first year degradation happening? It's because of the light induced degradation, LID. It's called a light induced because of a lot of optical issues and all. This degradation happens. It's called a light induced degradation. So LID is an important term you have to learn. Another term I will tell you, PID, potential induced degradation. It is nothing connected to your module degradation. It is because of, it's connected with the module degradation. It's kind of not the usual 0.6% or 0.7% degradation. PID is a different term. I remember when I was with the consultancy earlier years, I had a consultancy assignment from Australia for completely evaluating the PID for a Hong Kong plant. So PID, that time the PID compliant modules were rare. That was back in 2011. Now the market is flooded with the PID compliant modules. The PID is happening because of the, just like as the word says, the potential induced degradations because of the EMF coming up in that particular solar module, because of the spaces in between, because of the frames, because of the other than the cell, there will be some space where from this cell, the EMF will be induced into the frames and parts like that, which will end up in current leakage. So remember these two terms, dear students. One is LID, light induced degradation. Second is PID, potential induced degradation. Fine. Okay. I told you about that 90% of output should be there at the end of 10 years, and 80%, it is 80%, or 80%, not 25% loss. It's 80% at the end of 25 years. So it should be 90% output at the end of 10 years. Even you have a LID, you will have 90% of output. So 80% output should be there at the end of 25 years. So 80% of its output will be there at the end of 25 years, the designed period. Okay, fine. Not going much into this. Okay. You have a lot of certifications for PV modules actually. Hannah, can I take another 10 minutes? What about you?
Yes, sir, sure.
Okay. Thanks for that, because I have a few slides. I think I will wind up shortly. I'll just quickly go with this. We have a lot of certifications for PV modules. Remember that these certifications, IEEE certification, International Electrotechnical Commission certifications, are very important for a PV module. I'm not detailing much on the design certifications of terrestrial PV modules. There are IS standards for that also. That IS has recently come only. Certifications like design qualification and type approval is very important. 61215, and you have environmental certification. You have salt mist corrosion certification. You have ammonia prevention of the resistance of PV modules to ammonia. So, and okay, I will quickly give some ice cream about some of the softwares, some from the drier side. Coming to a soft side, I will recommend some softwares for you guys. Just download PVSYST, PVSol, Homer Pro, Red Screen, SAM. All these are softwares, very interesting softwares. You can download from the trial versions of PVSYST, PVSol, Homer Pro, Red Screen. SAM is free actually. SAM is a software from National Renewable Energy Laboratory, USA. It's a freely available software which you can download and play around it. You can even simulate a solar power plant for your rooftop. Okay. And okay, coming to, I will just, this also I will go through it just before my conclusion. I was telling a lot about the grid connected plants. I will give you a small workshop. You take your notebook, if you have one. Tell me if you have a notebook with you, if anyone at home. Do you have any notebook with you? I won't confuse much. Very good. I will give a small workshop for you, an off-grid solar plant battery sizing. It's very complicated that to size a off-grid solar power plant. You have to size your battery, you have to size your solar PV array, you have to size your inverter. Okay. And your balance of system. I'm not going much into your balance of systems like cables and all. I will just size your battery, module, and inverter. Okay. Fine, let us start. I'm assuming that this is a quick slide only because I cannot write here. So I'm not using any augmented reality, as I attended some sessions from PES itself. So if you have an augmented reality, I can kind of live demonstration. Maybe I will try in the next session. So I'm just assuming that you have different, your consumer devices, appliances like a fridge, TV, washing machine and all, which will add a total of 4 units per day. Okay, 4 kilowatt hour, means 4,000 watt hour. So I'm not going to the spreadsheet of your appliances on the first row. The connected load of these appliances in the second row, the period of operation of the third row, and the total watt hour coming, and adding up the watt hours. I'm just assuming that I am getting a total of 4 units or 4,000 kilowatt hour, 4,000 watt hour. Yeah, 4,000 watt hour means 4 kilowatt hour per day. Okay, this is my assumption. So take it like that. So this you calculate based upon a spreadsheet. By listing your appliances, you calculate your connected load and your working hours and total it up. Okay, perfect. I'm just sizing the battery. I'm just assuming that my system voltage is 24 volts. You can have the thumb rule is up to 1,000 volts, up to 1 kilowatt peak of solar power plant. You can go with a 12 volt system or a 24 volt system, and even 24 volt system you can go up to 2,000 watt or 2 kilowatt peak or something like that. And above that you have to go better that you go for a 48 volt system. So 48 volt system. So I'm just remembering, I'm just assuming that 24 volt system for this system, for this plant, and dividing this 4,000 watt hour by 24 volt. And I'm assuming that my inverter efficiency is, this is system voltage, inverter efficiency is 0.8. I'm going for a lower efficient inverter. Nowadays, when you go for MPPT off-grid inverters, you will get around 0.9 above, or even you are getting 90% efficient, 95% efficient inverters. But your grid connected inverters will be more than 98% efficient. All the international inverters are more than 98% efficient. So this is an off-grid inverter, very less efficient inverter. I took what is DOD, depth of discharge. Depth of discharge. What exactly you are taking up from the battery? Your depth of discharge, I assumed at 0.7. So I'm just dividing it for your convenience, for quickly giving you the results. I assume that I got, based on my consumption, I got a value of 297 ampere hours. I assumed it at 300 ampere hours. And I didn't multiply this with my autonomy. You have to multiply in the numerator with your autonomy, which you can do here, like here you can multiply with your autonomy. So here I will put my autonomy as one day autonomy. So I will get the same figure only, right? So for critical loads, and what you have to do is you have to critical load. For example, in a very remote tribal colony or a hospital use, you have to multiply with your autonomy. Autonomy means how many times your battery bank is needed. So for critical loads, you have to go for even 3 for a very remote tribal colony or a. I remember when we designed the microgrids of 12 numbers of microgrids in remote tribal colonies, we took an autonomy of 3 days. So 3 times of battery we sized, because if there is a prolonged rain, that system will be charged for giving power to the needy people. Okay, perfect. So sizing the PV array. How you size the PV array? So the first class is over, first session is over, second session. Your total whatever divided by your VOC, open circuit voltage, then I'm just assuming that you have 30% of losses, including your module losses and derating losses and temperature losses. I added everything into 30%. So I put 0.7 in the denominator. This is my module VOC. I got 153.61 ampere hours. So I'm just assuming a solar PV. This is the total ampere hour requirement. I'm just assuming a solar PV module output per day. I'm taking a PV module, a typical old PV module of 250 watt peak. From here, I'm taking this short circuit current and my values on current. Short circuit current 8.96. I took IMP, I think. Okay, roughly this comes to like that value also. So I will get around 44, 45. So single PV module output, I am getting 40.6. I'm just calculating the number of parallel modules. So total ampere hour requirement was 153. Then I divide with a single module output. Why I took 5 hours? Because 5.5 or 5 is the average sun peak hours in Kerala, right? It will be 3.5 if you take a site in Hamburg, Germany. Or if you take Y3, you will take 4 hours. So I took 5 hours because I live in Trivandrum. So I divide this single module output. So 153, the total ampere hour required by single, I will get 3.7. I rounded it to 4. So this is the number of parallel modules. So I got the number of parallel modules. And the system voltage is, so I will go for a series module only. One module in series only. So I will get a system with 4 numbers of 50 watt peak modules and a battery of 300 ampere hour 24 volt system. So roughly giving you an idea of how you size a PV module, a solar system, where the battery sizing will be based upon your total watt hours divided by your system voltage and your battery efficiency system voltage and your battery efficiency and your inverter efficiency and depth of discharge. And their PV array will be estimated by this. It can be just giving a thumb rule of how the sizing comes. Okay, perfect. So I'm not going much detail into some of the software side here because the time I took a lot of time on my design concepts and all. These are some of the pictures or slides from a PV simulation. I request all of you try with the PV Sol or any kind of softwares. Play around it, learn a lot of things. I'm not giving much on the instruments and specifications and certifications. Thought of giving you much on the design concepts, especially on the basic design concepts as younger students and all. With all this, I think I may wind up with I'm not going much sessions because I took already more than an hour on lighting protection and earthing practices. So I'm just telling, it's easy for us to go for solar rooftop. We have more than some earlier study itself gives more than tremendous potential, more than 31,000 megawatt of potential in Kerala. With the rooftop only, both industrial and domestic rooftop. If you tap 10% of that, you will get more than 3,000 megawatt. I used to say this in every presentation. So very easier to get generation from this. And with this, I'm winding up. I think I took a lot of time. So you have exams. Anyway, you can approach me or write to me with my IEEE mail or ANERT mail. I'm just winding up. And now out to you for any questions and all.
Thank you so much, sir. The section was really informative. Now let's have the Q&A. If anyone have any doubts or questions, please turn on your mic or drop it in the comment box.
Yes, you can.
Please unmute and ask directly. Or I think if they have anything in the chat box, Hannah can collect and ask me. Come on. I invite younger students to ask your even crazy questions. It's okay for me. With a couple of questions, we will wind up because we took more time. So we have a huge audience here. Hannah, all of them from the college?
No, sir. From different colleges.
Oh, okay. Great. Any questions, please? Or you can write to me, Ajith Gopi at IEEE.org. On the questions coming, or your doubts, or Hannah can collect it and send to me. I think nobody is coming up. It's too late.
So I think there is no doubt.
Very good. No problem. I think all are into their exams and all. So I think, Hannah, we can wind up the session now because it was already planned for 1 hour.
Yes, sir. Thank you so much, sir, for taking the session. It was a wonderful session, actually.
Thank you, Hannah. Anyway, thanks for having me.
Sir, even if this meeting exceeded time limits, it is good. It is good that you took the meeting and this class very well. Thank you.
Thank you, Jindo. I think Nitin, thank you very much. Because it's like if I wanted to teach you on these aspects, design aspects, I thought of sharing some design thoughts, especially tilt. What is tilt? What is orientation? Where shall I orient my solar PV module to south, or shall I orient it towards west? So what is the tilt should be given to my solar module? What is fixed tilt? So what is, so that was my interesting, my thought. So that's why, so I have some questions coming up. Very interesting. Samath Prateep, you can chat, you can write on the chat box. What is your opinion about using lithium battery for solar charging? Very interesting question, Samrat. Triple student actually. Actually, in off-grid systems, we generally use lead acid batteries. Traditionally, in the off-grid systems. Nowadays, the trend is changing. What is happening is a lot of lithium-ion batteries are coming to the industry. I would say that things are changing to a distributed energy resource world where battery backup is also there. Because a lot of batteries you need for that. So you cannot use a lot of usual lead acid batteries for that purpose. You need a lot of advanced batteries. And over the years, I would say that from the latest statistics, for the last 20 years, the lithium-ion battery cost has come down to 80%. Okay. And a lot of international and global and national companies are there where they are investing on the research on lithium-ion batteries, especially on different types of other kind of additions on the same site. A lot of innovations are also happening. I know on Vision Mechatronics based, a company named Vision Mechatronics, one of my friend, Dr. Roshni Gupta, she is actually heading the Vision Mechatronics. She started her organization 10 years back. They have a very intelligent product with them, like a small a smart device which can immediately power your remote areas and all suddenly. So these are the intelligent, any kind of intelligent applications comes with a battery. Even for your small appliances like your mobiles or any other kind of devices will have a lithium-ion battery or lithium pyrophosphate battery. So it will be very interesting to have a lithium-ion battery on board, even for a solar plane. You might have heard of solar impulse experiment from the brothers from Switzerland, Andre and team. They used lithium-ion batteries in aeroplane in their first solar impulse flight. So lithium-ion batteries are making wonders. Of course, lithium-ion batteries are used for the grid-level storage systems in heavy utility scale, large solar power plants, even in distributed energy sources. In distributed rooftop systems, what they are using is, you might have heard of our Elon Musk, the innovator, the entrepreneur, the famous entrepreneur who has the solar city company is there. They have the Tesla car is there. So they have a power wall. It's called a power wall. Power wall is a battery actually. For example, in California, if you want to connect a solar system, you need to have a battery as well. A grid level or grid storage level battery, where the battery will compensate with the grid disturbances. Whenever there is a dip in the grid, it will compensate. Oh, okay. Any other questions? You can write on the chat box or directly ask. So in any language we can ask. Malayalathiലും ചോദിച്ചോളൂ. Please. Okay.
Okay, thank you, sir. I hope there are no more doubts. Now I welcome.
Sir, actually, one more question arose in the chat box.
Oh, about quantum battery, I don't have much idea. Sorry, Deepu. I'm not an expert on battery. I think anyone from this group can tell more about it, and some of my colleagues can tell about quantum batteries. I don't have much idea about it.
Okay, fine, sir.
Okay.
Now I welcome Anubama Monsi, Joint Secretary, IEEE SJCET for vote of thanks.
Good evening, guys. I hope I'm audible. First of all, I'd like to thank you all for spending this Friday evening to attend this session. Thank you, Ajith sir, for sparing some time out of your busy schedule and delivering such a wonderful and enlightening session. It was truly informative and engaging. I'd like to thank Arun sir, Branch Counselor for IEEE SJCET, our Principal Dr. G. Dept, all our supporting faculty and our management for helping us to execute this event successfully. I also thank our chairman, Mr. Alban Thomas, all our ExCom members and the entire team for supporting us to conduct this event. We would like to present this virtual memento to you, sir, as a token of our sincere appreciation. We wish you all the best in your future endeavors, and thank you once again, sir.
Thank you. Thank you for your good words. Thank you, all of you. Thank you all the very inspiring welcome given to me. All the best to the active volunteers here, IEEE and IEEE PES volunteers. On behalf of IEEE PES, also I would like to congratulate you for conducting this session. This session was actually, it's actually a workshop kind of thing we have to organize, but still I feel like as young students, sort of giving you a small talk on this, to give you some spark on design, so that everything should be scientific. So you have to depend on science. To give you some spark in your minds, that was my intention. Wonderful. You have done a lot of participants from different colleges. I'm privileged to be here. And thank you, my colleagues, some of my colleagues and younger graduates and professionals also attended this session. Thanks to them also. Again, thanks for having me. Have a wonderful evening. Bye.
Thank you, sir.
Thank you, sir. Thank you for your good words and your time. Thank you so much.
Thank you.
Thank you, sir.
Thank you.